Hey everyone, my name is Bowen Li. I'm a Apache Flink committer and a senior engineer at Alibaba. And today I'm so glad to be here to talk about what we have been working on Apache Flink and stream processing. So here's the agenda today. We will go over some use cases in Alibaba and other companies. We will do some recap on the core concept or philosophies and characteristics of Flink to see what makes Flink so successful in stream processing world. And we will then take a look at what we have been working on beyond stream processing. Okay? Alibaba Group is the largest e-commerce company and ecosystem in the world. We are, with regard to GMV, we are about twice as Amazon annually. We have like consumer-facing website like AliExpress, Taobao, Tmall, B2B website like Alibaba.com. We have the largest logistic network in the world called Cainiao. We have the largest public cloud in East Asia, Alibaba Cloud, and the largest private financial institution and financial. Flink has been really widely adopted within Alibaba. It supports all the business units' real-time computation, as well as all the offline and online search and recommendations. We also provide Flink as a public service on Alibaba Cloud called RealTime Compute. Just to give you some sense of how big Alibaba is, so among the 365 days of a year, there's a single day that matters the most called Singles Day Global Shopping Festival on November 11th. And as you can see from the charts from 2016, the GMV of Alibaba ecosystems of that single day has surpassed the Black Friday shopping season across the United States and has been surpassing ever since. We just had a really successful Singles Day shopping festival last week, so here's some really hot and fresh data. On that single day, on the first 21 seconds, we made $14 million sales. On the first 96 seconds, we made $1.4 billion sales. And of that single day, the total sales is $38 billion US and generates about like 1,000 petabytes of data in 24 hours. And at the peak of that traffic, we support over 500,000 transactions per second. Flink support all this real-time computations really smoothly without any downtime. At the peak traffic, Flink handles about 2 billion events and about 3 terabytes of data per second, which is more than doubles from 2018. I'll just go over a couple Flink use cases within our company. The first is online machine learning. So whenever users interact with our app or website, their events generated from their behaviors got hit our search service or recommendation service, and then the data flows into our online machine learning service, got ETL'd, sampled, then we do real-time training and model validation testing and deploy it to score and scoring service and then feed back to the search and the recommendation. So all that happens in real time. The service can handle hundreds of millions of events per second with over 100 billion features. The end-to-end latency is within seconds, and all the training and model update happens in real time. The second use case is RealTime GMB Dashboard. So on the single-day shopping festival, Alibaba will publish a globally available dashboard that anyone can access. And you can query, like, you can see how much is the GMV from the beginning of that day to that very second. So this is like a pretty simple architecture of how we do that. So basically, all the business units will submit their transactions into some some central hub, and we use Flink to do exactly once processing on those transactions within sub-second latency. Output the results, the GMV into HBase, and have the dashboard query it. Lots of companies are leveraging Flink to do fantastic stuff. For example, Netflix and Xiaomi are also leveraging Flink for real-time AI. All those ride-sharing apps are using Flink to do dynamic pricing. For example, on Uber app, whenever you type a destination, then you immediately get back an estimated price, right? That considers into the distance, all the drivers available, all the consumers that want to request a cab. All this complicated computation are backed by Flink in real time. Financial institutions are leveraging Flink for fraud detection, risk management. Consumer-facing companies are using Flink for real-time analytics. And as Flink becomes the de facto standard for stream processing in the industry, it got offered by all these public cloud players as public services. For example, in the United States, Kinesis Analytics are backed by Flink. Next, I want to have us all together recap what Flink is about and what Flink is so unique and why it has been so successful in stream processing world. Here's a typical the typical pipeline you would build with Flink. You basically have applications or devices generating events, input it into some streams, or the data has been sitting in the distributed file system. You have Flink query them, process them in real time, and then emit the results to the downstream. So what is Flink? Flink first is about stateful computations. Why does state or built-in state matters in stream processing world? First, when you do especially complex stream processing, you always want to process a record according to a context, right? You want to look at some historical behavior and then decide what to do with this record rather than just processing it. So in order to look up into the context, you have to have this context sitting somewhere for you to query. That is where the state comes into play. And of course, you want this state to be as local as possible, to have this data locality, and you can save the expensive network I/O, and thus gain a much lower latency. And last, you want full control of the state, right? You don't want to be it's completely external without control, because upon failures, you want to be able to roll back in order to support the exactly one semantics. Fortunately, Flink supports built-in state backends out of shelf. And our state backends support rich arbitrary data structures, for example, map or lists, or nested data structures in a fully fault-tolerant way. We provide two state backends. The first is in-memory scalable backends. So it's used for faster in-memory queries, but if the state just got really large, it can be spilled to disk. And we also provide off-core RocksDB state backend for terabytes of state data. Then Flink Flink applies the stateful computations to event streams. And event streams actually means a few things here, and I want to walk you step by step. The first is, according to Flink's philosophy, all your data is data streams. So when we talk about batch and stream processing, we are actually just talking about some mechanism. The fundamental difference under the hood is actually your data. So when you see batch processing, you usually have all the data at your hand, and you know how large the data is, where it is, right? So in this case, it's actually just bounded data streams. On the other hand, when you do stream processing, the data just keep flowing in. You don't know when the data will end. So in that case, it would be unbounded data streams. And that's we believe is the key difference between batch and stream processing. And thus, technically, all data processing is stream processing. Second, different from most of other open source technologies, Flink is built with this streaming first architecture with pipeline execution. So in pipeline execution, record just flowing in and through the system without any delays. That gives us the benefits of extremely high throughput and ultra low latency. This is super different from a batch first system with staged execution, where all the data flows into our system but executed in batch in stages. And you cannot proceed to next stage until the first stage complete all your data processing. That caused extra latency, and the advantage of this pipeline execution cannot be gained with so-called mini batch mechanism. Last but not least, event comes with time. Lots of open source technologies, they usually just support processing time. Well, we would argue that event time actually matters more in most cases, because event time is when the event actually happens, and usually it has a timestamp embedded into the event JSON, right? And processing time is just when the event comes into your system and got processed. So usually it doesn't really mean anything. And when you want to do logic with times, you look for some advanced semantics. For example, window aggregation, like sliding window, tumbling window. You want to do sessionization, like you want to do a session window on that, and you want to be able to join streams based on some time. The processor should also be able to handle out of order data and late data. Fortunately, Flink support all these comprehensive data time semantics from the very beginning. Flink is expressive. So we provide users with this layered API. So on the top, you can have a SQL or a table API if you don't want to program Java, Scala, or Python. That gives you a fully self-service environment. You don't need to understand how Flink handles it. It just did the magic for you, right? In the middle, it has the native stream processing API where you can write Java, Scala, or Python. And on the bottom, you have the process functions, which expose lots of the fundamental building blocks to you, like event, state, times. So you can do, you can manipulate times and state all by yourself to do very precise control. Flink is scalable. So as I mentioned before in our use cases and the other companies' use cases like Netflix, it's normal for Flink to handle trillions of records per day with terabytes of state. And it can run thousands of cores, no problem. We pay really lots of attention to make it operationally friendly. You can deploy Flink anywhere. On Kubernetes, Yarn, Mesos, or stand alone on your computer, no problem. You can deploy it however you want, like per job mode, session mode, with high availability setups. Last but not the least, Flink guarantees to recover from fault and can do everything in exactly one semantics. When some open source technology claim they are exactly once, actually they are trying to confuse users with this, with some key differences laying there. So there are two kinds of exactly once semantics. The first is if they just talk about the exactly once within their system, they are actually talking about exactly once state consistency. It means each record flowing into your system impact and only impact the state of this logic once and only once. So that's what what's normally the exactly once means. And if you want to have this external connectors to interact with, let's say, Kinesis or Kafka, these external streams, then you are talking about end-to-end exactly once. So Flink actually support both very well from the very beginning. If you use like Kafka transactions, you can achieve end-to-end exactly once. You read a record only once from a Kafka stream, and write to a Kafka stream only once. And Flink has this on-the-fly checkpoint and save point mechanism that doesn't sacrifice much of this performance. So Flink in a nutshell, let us recap this, is stateful computations over event streams in an expressive, scalable, operation-focused, and exactly once and fault-tolerant way. So as the last part, I want to be to talk to you about what the community has been working on actively recently in this different field. Let's look at the unified data processing or batch processing first. So why does unified processing matters to companies and teams? Let's recap this called classic Lambda architecture, where you usually have two pipelines, right? On the bottom, you have an offline pipeline that reads some historical data from a distributed system, file system, emits some historical data results, and then you have this online pipeline where the stream processor reads from a messaging queue or PubSub system, emits this real-time results, and then you combine them together to output to downstream. This architecture was invented by the author of Storm. Is because this old style, like stream processing engine, cannot guarantee correctness of online part. Thus, you have to periodically have this offline part to correct the results of the online part. Well, that brings lots of headache to the team. For example, for the infrastructure team, you have to operate more than one infrastructure and to monitor and be on call on it. Developers have to maintain their code and learn more technologies. And from the business perspective, you have two code base, and you have to keep them in sync, right? You change something in the online part, then you have to change it on the offline part. If you forgot, oops, you are like screwed. So why Flink? As I talk a little bit about Flink's perspective on the batch and the stream and unbounded and the bounded data stream perspective, it's natural for us to use Flink to solve this problem because Flink is streaming first, and we believe batch is just a special case of streaming. Well, even though Flink is born with this vision, before Flink 1.8, the stack doesn't really look so. So on the left hand, you can see before 1.8, we actually have a unified API on the top, but during the execution or the stream or on the Java Scala API layer, we actually have separate APIs, right? You have the data stream API and data set API, and they will actually generate different execution plan to be run on task managers. Fortunately, in 1.9, we completely changed that. On the right side, you can see we unified the planner and the down the stack layer to be a single stack. So you have this SQL and table API, then you have a single planner to optimize both stream and batch use cases. Then it generates a single unified stream transformation with stream operators to be able to run on Flink tasks. Here's some TBC DS benchmarks that we run within Alibaba. So this is run with Flink against Spark. So Blink is an internal fork within Alibaba of Flink. And as of Flink 1.9, Blink has officially become part of Flink. So beyond just batch processing, we go like 2 steps ahead. One is we provide this Flink and Hive integration to tackle the data warehousing use case. In 1.9, we launched this initial integration with some limited support on some limited Hive versions. But in 1.10, which is going to be released in this December, we provide full integration on read, write, and UDFs on all major popular Hive versions. We also natively integrated Flink into Zeppelin. So if you download Zeppelin right now, you can run Flink queries, SQLs natively without any problem. Next, I want to spend a little bit more time talking about machine learning, AI, and deep learning. Let's go back to the Lambda architecture for machine learning. It's similar to the one for data processing, where you have this offline training pipeline and online training pipeline. And somewhere you combine this the dynamic model from the online pipeline and the static model from the offline pipeline together, deploy it into production to do inference. Normally, people would do nowadays is using Flink for this online pipelines pre-processing, and then at the end deploy the model to Flink to do production inference. And how we want to solve this problem is as simple as running Flink everywhere. So you have a single stack and a single code base and the infra to interact with to gain all the benefits. How can we do that? If we separate this pipeline into stages, then we can look at each stage has separate requirements and how Flink can support all that, right? At first, you have data acquisition. In this part, you will require some rich connector support where all the data, you can access data however or wherever you want it. And also, you want to have this data set management. In the pre-processing part, you will require stream and batch unification and some strong SQL and API support. In model training, you will have enhanced iteration. And you would want some out-of-shelf machine learning libraries and also some deep learning integration techniques. In model validation and serving, you would want the framework to handle serving, registry for you, and also be able to roll out and roll back on demand. At the inference phase, you would want to have the online evaluation. And just as a fundamental thing for all this phase, it will require some kind of machine learning pipeline mechanism and also strong Python API support. And fortunately, all the green part has been supported in Flink. The brown part, we are actively working on them. And actually, most of the company right now, like Netflix, they just develop these things themselves. It's not that hard to do. Then we'll look at some of this red part in detail. First is machine learning library. In 1.10, we completely rewrite these machine learning libraries to make it based on machine learning pipeline, which I'll talk about in a minute. And we provide some battle-tested algorithms for users to leverage. We introduced a brand new machine learning pipeline. This is basically mostly based on a paper. So there will be 2 kinds of operators in machine learning pipeline. One is transformer, where you ingest the data and output data. The second is estimator, where you ingest the data and output a model. So in this case, you will see you have this training phase where the table 1 flows in. Got trained by an estimator into a model pipeline, and then you just deploy the model pipeline to the inference production environment to do whatever you want. Deep learning pipelines. How people usually do this is basically the same as the machine learning ones. Is you use Flink for data acquisition and pre-processing, but you use TensorFlow cluster for like model training, validation, and serving. And you have this parameter tuning loop in the middle. The structure usually like this. You have a Flink cluster, and when you pre-process the data, you emit it to some distributed file system or Kafka message queue as external infrastructure, and then ingest it in your TensorFlow cluster to do all the training. It has lots of headaches. Is that you have 3 structures to manage. You have this intermediate external dependency and all this like Lambda headaches you already have in the previously mentioned slides, right? So the solution is simple. As I mentioned, use Flink to do everything. But how? Basically, you would run TensorFlow within a Flink cluster. So it will look like this. It's a single Flink cluster. The data from Flink got pre-processed with good quality. We just flow directly into the TensorFlow operator that's living aside from Flink operators. And it actually fits perfectly into the machine learning pipeline we proposed, right? You would see Flink as a transformer and then the TensorFlow operators as an estimator. So it fits perfectly. Last but not the least, serverless. Lots of companies are using serverless, and of course, like AWS Lambda. This serverless idea is basically it's event-driven. So some event happens, triggered your Lambda, and you do something and emit it to the downstream. It has lots of benefits. It's elastic. It can scale up and down without problem on demand. It's pretty lightweight. You just roll the code, doesn't need to worry about how to deploy it or anything, and the resources consumed is pretty limited. Well, it has lots of challenges too. For example, all this off-the-shelf Lambda solution doesn't provide a good state. So you have to manage your own external state to worry about the consistencies, the network I/O, the external storage capacity. And it's a little bit hard to build complex logic. Let's say, what if you want to chain 2 or more Lambda, AWS Lambda functions together, right? You have to emit the data to like Kinesis and then ingest it in another Lambda function. So let's summarize what we want for serverless. It's event-driven. We want a good management for state. And we want to be able to compose some complex logic with serverless. Doesn't that sound familiar to everybody? It's stream processing, right? So I'm happy to tell you about this new project called State Function, which is announced October this year in Flink Forward Berlin. Upon last week, it's officially become part of Apache Flink project. So please go and check it out. So what this project is about, building serverless functions on top of Apache Flink and have Flink to manage all this state and composition for you. So yeah, that's all the content for today. Thank you very much. You can get in touch with us on the mailing list or Twitter. Do you have time for questions? Okay.
Could you comment on comparing the Flink versus the Spark? And
you mean comparing these 2 frameworks?
Yeah.
I mean, I'll just mention a few ideas, but for like full comparison, you can search online, or I highly recommend to run some to do some experiment with 2 frameworks, because sometimes there can be like false claim or misleading content. But basically, first Spark is born with like batch first in mind. Flink is streaming first, so there is like fundamental difference on the execution, like pipeline versus stage. And also with regard to functionalities, Flink supports all the comprehensive like time semantics and operations where you can't do that in Spark. Even though in Spark structure streaming, they create this ticket saying like they are doing this a long time ago, but it has been like sitting there about like 2 years. So I highly recommend to do some experiment yourself. Try to run some production logic and see where it goes. Yeah.
Me again. So you mentioned extremely high throughput, and you showed some pretty impressive comparative results there. The conventional wisdom for years was that because Spark was a micro-batch system.
Okay, sorry. Can you say it louder?
Sorry. You mentioned sort of extremely high throughput from Blink, I guess, which is really impressive. The conventional wisdom for years was that because Spark was a micro-batch system, for sort of mechanical sympathy reasons, and also for kind of like stream fusion compilation reasons, it could achieve higher throughput. But I guess now that there's a unified like planner compiler in Flink, now it becomes possible for Flink to do the same kinds of optimizations, right? Is that true? Or I'm trying to like what's the reason for the massive increase in performance that we're seeing?
Yeah. So the question is why if Blink like performance actually better on the batch side, right? So yeah, as I mentioned, the execution model is fundamentally different, and also we add lots of optimizations with around like batch and stream processing, for example, vectorization, all that. So yeah, it's just gives us this. I guess it's just some advantage from the very beginning. Yeah, it's just you need to like kind of tune it and unleash the potential. Yeah.
Great presentation. My question is about how, obviously you believe that Flink is kind of should be used as a universal computational runtime across all these different computations, but I guess my question is how approachable the system is in terms of what's the wide dynamic range of users who can successfully interact with it, meaning like you put a data scientist in a Jupyter notebook, they start to explore stuff. Like, can that person successfully interact with Flink within the Alibaba organization? Or what wide swath of builders can successfully work on the system?
So the question is, are there any like successful use cases for data scientists to use Flink on notebooks?
It's more, that was like an example of a type of user who is responsible for doing ETL and building models. I'm not totally focused on the notebook example, but just like what can a wide variety of people successfully build on this system, or is it kind of a narrow set of data engineers who really get streaming in their core and this kind of advanced computational model?
I'll try to answer answer that. First, the stream processing really has some threshold for you to enter. For example, you need to understand some complex logic like state, time semantics, all that. This is a little bit different from batch processing, right? So you do need some good understanding and spend some time learning about it. But with regard to the use cases and the people, whether they are successful, I would say so, yeah. It has been like adopted very widely across the industry, and I recommend you probably look at like Flink Forward, some videos to see how those people are leveraging that. I would say that they are pretty successful with Flink.
I think we could take one more question. Or 0. That works. All right. Let's thank our
Thank you,
speaker.
everyone.